Hello everyone and welcome to Techie. Today we're going to cover the Global Network Challenge, your data's digital passport, how routers direct traffic, the packet's journey, arising at the destination, and finally, the Internet's invisible architect. We are going to demystify Layer 3 of the OSI model, the network layer, by following one single piece of data on its incredible journey across the Internet.
All right, first up, let's just talk about the massive problem the network layer was even designed to solve. See, the Internet, it's not one giant network. It's actually a network of networks. We're talking millions of them. The huge challenge Layer 3 tackles is how to build a universal postal service that can connect all of them no matter where they are.
I mean, really think about this for a second. When you send an email, you're not opening some kind of direct private phone line to the other person, right? No, you're dropping a letter into this massive global digital mail system. And that letter, it gets chopped up into tiny little pieces called packets. Each one of those packets has to navigate this incredibly chaotic maze of networks to find its one specific destination out of billions. So how on earth does it not get lost? Well, that is the fundamental question that Layer 3 answers.
You can think of the network layer as the GPS for your data. Its main job is just to move these packets from a source host to a destination host, even if they're on completely different networks. And this whole process, weaving together millions of separate networks into one giant seamless web, that's called internetworking. It's literally the inter in Internet.
Okay, so for a packet to travel, it obviously needs an address, just like a letter you'd put in the mail. But this is where it gets interesting. We're talking about a logical address, not a physical one. It's kind of like a digital passport for your data.
And it's so important to understand the difference here. You have your MAC address, which is physical. It's like a serial number burned into your device's hardware, and it's permanent. It's only used for local delivery on your same network. But then you have the IP address. That's a logical, software-based identifier. It can change. It's used for global routing across different networks. So think of it this way. The MAC address gets a package to the right apartment in your building, but the IP address is what gets it to the right city in the first place.
You've probably heard of IP addresses, but you might not know there are actually two kinds. We had IPv4 for a long time. It gave us about 4.3 billion addresses, which seemed like plenty back in the day. But we ran out. So now we're transitioning to IPv6, and the number of addresses here is just staggering. We're talking 340 undecillion. To put that in perspective, that's enough to give an IP address to literally every atom on the surface of the Earth, and you'd still have plenty left over. And it's not just about having more addresses. IPv6 also has some really important upgrades, like built-in security.
So, the packet has its address. Its passport is ready. Now what? Well, it needs a guide for its journey, right? And that's where routers come in. These are the brains of the network layer. So what is a router? Well, it's a networking device that forwards data packets between computer networks. Think of it like an air traffic controller, but for data. It uses something called a routing table to figure out the best path for every single packet. These are the essential devices that connect all the different networks together to form what we call the Internet.
And these things work incredibly fast. Inside every router, there's a forwarding module that's just constantly working. It examines a packet's destination IP address and then immediately looks it up in its routing table to see where to send it next. It's a non-stop process.
And this right here is a routing table. It's basically the router's map of the Internet. It tells it which path, or next hop, a packet should take to get one step closer to its destination. For example, if it's going to a network the router is directly connected to, that's easy. If it's going to another known network, it sends it to the next router in the chain. And if it has no clue, it just sends it to the default route, which is kind of like the main on-ramp to the Internet highway.
So yeah, it's a really simple three-step process. 1. Examine the destination IP address in the packet header. 2. Consult its internal routing table for the best path. And 3. Forward the packet to the next hop router. And this simple loop happens millions of times a second in routers all over the world.
Okay, so now let's follow our packet as it actually hops between these routers and deals with some real-world problems, because the journey isn't always smooth.
You see, not all networks are the same. Some roads are wider than others, right? Well, the same is true for network links. The largest size of a data packet that a network link can carry is called the MTU, or Maximum Transmission Unit. For Ethernet, which is super common, this is usually 1,500 bytes.
So what happens if a packet is larger than the next network's MTU? Well, the router has to break it up into smaller pieces. This is a process called fragmentation. And it's what allows these large packets to travel through networks that can only handle smaller data sizes.
Now, to manage all this, the IP header has specific fields that act like instructions to make sure all these fragmented pieces can be put back together at the end. You've got the identification field, the flags, and the fragment offset. Together, they basically tell the destination computer, hey, all these little pieces belong together, and here's the order to reassemble them in.
But, the journey isn't always smooth. Sometimes things go wrong. When a router has to drop a packet, it doesn't just vanish. A protocol called ICMP, the Internet Control Message Protocol, sends a message back to the source to report the problem. It's kind of like the network's return to sender stamp.
And these messages are super important for network diagnostics. Things like destination unreachable. That means a router can't find a path. Or time exceeded, which means the packet has been hopping around for way too long. These are crucial for tools that you've probably heard of, like ping and traceroute. They rely on ICMP to figure out what's wrong with a connection. All right, so after successfully navigating the entire internet, our packet finally arrives at its destination network. The journey's almost over.
At the destination computer, all those fragments are put back together into the original datagram. Then, the network layer does its last job. It strips off the IP header and passes the nice clean data up to the transport layer, layer 4. And that's it. Its job is done.
So let's just step back and summarize the absolutely critical role the network layer plays in pretty much everything we do online.
Okay, so let's recap the key takeaways. The network layer's core functions are, first, logical addressing, which provides those unique, routable IP addresses. Second is routing, which intelligently figures out the best path across all the networks. Third is forwarding, moving the packets hop by hop toward where they need to go. And finally, internetworking, which is the magic that connects all these independent networks into a single global internet. These 4 things work together to create the seamless connectivity we all rely on every single day.
And that pretty much wraps up our journey. But it does open up some new questions about the future. As we move towards a world that's fully on IPv6, how is routing going to evolve to handle literally trillions of connected devices? It's something to think about.
So if you found this helpful, please do me a favor and like this video, and of course, subscribe to Techie for more explainers just like this one. We'd love to hear from you, so drop a comment below with your thoughts or any questions you have. Thanks for watching.